All right, thanks everyone for coming. I come all the way from California, and I'm glad that I didn't have to learn German first. But this is about my journey that I started in 1986 to develop an operating system software. I've always been fascinated with operating systems, particularly multitasking operating systems. And this is about first starting in the software and then in the hardware. So in my career, I've always been designing hardware and writing software for other people or other companies. And they always had to meet a business need. And now that I'm retired, I don't care about the business, whether it make any money. It's just about having fun. All right, so in this presentation, I'll be sharing the experience, as I mentioned a second ago, and I'll make the case that an obsolete disk operating system can still have the purpose of teaching basic OS functions and skills, as well as providing a lot of enjoyment and providing an outlet for creativity and shared experiences. So I know in several careers, they've asked me, what do I like to do the most? And I have several times confessed that I love to troubleshoot. Some people fall apart when they have to troubleshoot because they can't make sense of what's going on. For me, I love the challenge. This is also, I'll make the case about how making any change and improvements with powerful modern troubleshooting tools can actually transform debugging from a chore into having a lot of fun. So why CP/M? The CP/M, I guess I'm going to go with the basis of not assuming that everybody here was around and knows what CP/M is. So for those that were, bear with me here. But CP/M used to be the dominant operating system for a period of about 5 to 7 years, where it was number one. And so it had its moment in the sun. CP/M also has a relative simplicity. It's possible that one person can know the entire operating system code. The code itself is 45K. And it is incredibly complicated, and there's a lot to it, but you compare that with the megabytes or gigabytes of a modern operating system that was written by thousands of programmers, and there's not a chance that it can be something that you can totally own. When I say own, what you see here is every instruction that's executed, I've either reviewed it or wrote it. And then the other thing is that since CP/M has long since been a commercial product, it's the company that owned the rights to it a few years ago basically said anybody can do anything with it. They completely released all rights to it, and you can even, if you can figure out a way to make money for yourself on it, they don't care. And so that's important, is to have the source code. I mean, you're not going to get a source code to anything from Windows or Macintosh, and even if you work there, they never let one employee have everything. All right, so I want to take a minute to think about, when I was putting this presentation together, I was saying, all right, in vintage computing, what is it that we actually do? And when I distilled it to a simplicity, I thought the word preservation. What we do is we preserve old computers, vintage computers, and if we don't, they'll just be lost forever. And the preservation is in two buckets. We preserve the user experiences. You see that all the time out on the floor. And we also preserve copies of the hardware. And then secondary to all that is that we share the experiences. So when you walk up to these booths and somebody has a game they found on an Amiga that no one else knows about, they're just very proud to show this unknown game. And I think all three of those things are really important as to what we carry forward. And if we don't do it, nobody else will. So my journey is about playing with and with computing experiences that can't be experienced without the technologies that are commercially available today. Going forward, there's never going to be an operating system as simple as the ones that were available in the 1980s. That's just a fact. Everything gets more and more complicated, and engineers are increasingly less and less in contact with the hardware. When a new processor comes out, chances are they're going to have a library provided to them that hides all that. It makes their job more efficient, and you know, they can get to a commercially viable product sooner. But for people like me, it ruins all the fun. So you know, another way to look at CP/M is what it was, and if you look at the progression of operating systems from the end of World War II, where the first digital computers came out, to the 1950s, computers didn't actually have operating systems. They just, every time you had something for it to do, you changed all of the software, loaded in a paper tape or a mag tape. In the 1950s, they began to see the wisdom of not doing everything from scratch. And there were operating systems, but they were all vendor proprietary. And a lot of customers really resented that. You would buy, if you bought an IBM, you then depended on IBM to write your accounting software. And they didn't have to worry about how, giving you a bargain. They charged as much as they possibly could. So in 1970s, Unix first appeared on a PDP-11 computer, but because Unix came from the phone company, and the phone company had, in the United States, had a federal judgment against them saying that they can't make money in the computer business. They weren't allowed to sell Unix. So they had to put it in the public domain. And so Unix didn't have a path to being a viable commercial product, at least initially. It basically took Berkeley to create their version and sell it, and later, Torvald did Linux. But Unix was kind of stuck, and so it wasn't really a viable operating system that was detached from the hardware. It was, but there just wasn't a way to use it. So in the mid-70s, Digital Research, I think 1975 or 76, they introduced CP/M, and the first implementation was on an Intel 8080 microprocessor development system, which we saw in the museum last night. It's an expensive system, and when you purchased CP/M, the sample BIOS they gave you was on that very strange hardware. So what CP/M contributed in its day, it was the first time that a commercial operating system wasn't tied to a vendor. And at this, coincident with that was the first microprocessors were rolled out. At the time, I was working for a mini computer company, and I can remember internally, they just considered microprocessors as these, low performance, perhaps toys, and they didn't realize that one day there would be no mini computers or mainframe companies ever again. But they acted like they were going to live forever. So with the 6502 coming out, the 8080, the Z80, 6800, and the 1802, the market was blown wide open. And so at the same time, not only CP/M, but those other microprocessors created a lot of startups in the United States and in Europe and everywhere around the world of companies that hope to make their fortune by publishing software for these new microprocessors. So these are pictures from my collection, and this one, one of the things that hadn't been thought out but that suddenly dropped into the laps of everybody that was in this business is, how do you put software on a diskette that only costs a few dollars and convince someone to pay hundreds of dollars for the software? Now, they needed to charge hundreds because development isn't cheap. And so the first thing that occurred was to use these really cool looking, I don't know, we call them slipcase bookbinders. And it was nothing more than just psychology. They looked cool to get you to pay the money that they needed. So I'm going to quickly go through stuff that I've collected over the years. T-Maker's like a like a Microsoft everything. Microsoft had an assembler. SLR came out with one that was many times faster. DBase 2 was a serious database program that businesses that couldn't afford DECs or IBMs would buy CP/M systems and use DBase. These are, I have a demo coming up on one of the spreadsheets here. Condor is another database company that competed with DBase that no one ever heard of then as well as now. Just lots of many startups that had dreams of making it big and never really getting too far. Perfect Calc tried to compete with SuperCalc and VisiCalc and never did. These are a couple of editors that I bought and within 5 minutes realized I wasted my money at the time. Now, when you, for a company that created a Z80 computer that wanted to sell them, you needed an operating system, and so they would license CP/M, which was inexpensive, and they gave you this book that you see on the left. And inside, it told you everything you needed to know in one book about this thick, how to create a BIOS, and and the BIOS just basically customizes the hardware that you want to use in a way that the operating system can use it. So CP/M basically abstracted the hardware and hid it from the application. SuperCalc, WordStar, they never needed to care about how the hardware actually worked because CP/M would hide that, and you helped it with the BIOS that you would write. And not long after CP/M was rolled out, about a year or two later, Digital Research released MPM, which was the multi-user version. Again, in those days, memory was still horribly expensive. CPUs weren't as expensive, but the rest of it was. And the idea that you could buy a single 8080 or Z80 system and have up to 8 users using it was a way to maximize economy. Altos Computers made millions selling 4-user MPM systems to all kinds of businesses. And that's, you know, I wanted to get a copy of it so bad in those days, but the license for it back then was $550, which was a lot of money back then. And I just simply couldn't afford on the money that I made to get that. But I kept my eye on it. In fact, a few, maybe 10 years later, an Altos employee said, you want a copy? And he printed the source code for me. But on paper, it doesn't help you much. Now, these are badges that I wore when I went to, I was working for a company that sold CP/M software in 1983. I'm putting them here just to show you that at one time CP/M had gigantic conferences. The one on the right filled Moscone Center in San Francisco with, I think it had 30,000 attendees. The one, CP/M83 in East, was just as big. In fact, I remember one of the Digital Research employees was standing next to me as we were looking out at the crowd, and he said, Chris, look at this. He says, can you imagine Microsoft ever have anything this big? Even I knew at the time that was kind of an absurd statement. But Microsoft was still selling the early versions of MS-DOS at the time, and they had a lot of room to grow, and they still hadn't had conferences this big, but they did within a year, and everything changed. So it's also important to understand what happened to CP/M. Basically the world changed, and CP/M didn't change enough. It never really had a serious path to getting in, graphics. Steve Jobs went to, Palo Alto and saw the mouse pointing computer that they developed and didn't know what to do with. But Apple evolved to, from the Apple II to the Macintosh. Microsoft, went to Windows, and CP/M was history by, like 1986 or 87. So for people like me, a computer hobbyist, what can MPM offer today? Well, it gives me a chance to learn the internal functions of how multitasking and multi-operating systems work. The principles embedded in NPM are the same as in Windows and Macintosh and Unix today. It's a preemptive multitasking operating system that every time it switches tasks, it actually prioritizes and figures out which to work next. It does not do what's called round-robin scheduling. If you did that, you would be very disappointed in the performance. It always makes sure that it works on the highest priority task while making sure that nobody hogs the computer. And the multitasking software is very complicated in assuring how that happens. And the only way you can learn it is to look at the source code and watch it work and step by step and say, oh, wow, that's how they solved that problem. And so that's tremendously education for me and stuff that I've always wondered about how they do that stuff. You know, getting back to what NPM can offer today, so learning is the inevitable byproduct, which greatly adds to the satisfaction and enjoyment. You know, I get bold and make big changes, and then nothing works, and then I spend, you know, sometimes weeks troubleshooting to figure out, you know, what's wrong. And I can tell you that most of the time I suspect that it's a bug in the original operating system. And when I get to the end, I get pretty humbled because I realize I put the bug in. So I can say that my software coding disciplines have been greatly enhanced because when you're sloppier than you should be, or you're not as sophisticated in your procedures, the person that pays is yourself. And so you have this tremendous incentive to document things. You know, I look at other people's code from the time and I see no comments and I say, wow, they didn't have to support it. They must have handed it off to somebody else who said, why couldn't they put some notes in here to explain what's going on? My source code, which I've published on GitHub, you can see that I've got far more documentation than Digital Research ever put in their version of NPM. In fact, what would happen is they would intentionally not document because, you know, if you license, like when Altos licensed NPM, they demanded the source code because they obviously spent millions of dollars, you know, with the rights. And Digital Research was so paranoid that they were giving away, or the source code would leak, that they had almost no comments, and the comments were very obscure. And I really suspect that what happened is they had two versions of the source code. One that they would keep internally that was noted properly, and another that they would give to sucker customers and who would think that they got the actual source code when they didn't. In the 1980s, you know, when I was in college, for a class, I had to buy this 8080 trainer. That was my first exposure. And then the big board one, I still have a copy of the ad that I saw in a magazine, $650 for a board this big that you have to assemble yourself. That was a lot of money. The same company updated it to support double density floppies and more memory, and I bought that for basically the same price. And then in 1984, this company in Los Angeles named WaveMate actually had this bold ad claiming that they were the fastest computer in the world. They weren't, but they had a really decked out single board computer that was about this big. It had, it's the only board I've ever seen that had Z80 DMA chip, which is, you know, 40 pins just like the Z80. And it was a 4 NPM 2 system. And I used that along with the next one that I worked on. You'll see in the slide that I sold it to an accounting firm who bought a copy of DBase accounting software, and they used it as a 4-user system. And it worked better than if they had 4 single computers because they all had to share the same database. If they bought 4 individual computers, they would be constantly moving files over or moving seats from desks. I don't want to work on this customer this week. And so wherever they sat, they could pull any of the customers. They had like several dozen clients, so they were doing bookkeeping for several people. And that worked out really well, and they used it for 6 years. The SPC, which stood for Southern Pacific Computers, was a Japanese company. They made this thing called a single board computer that was much smaller, using the 64180 or Z180, which was an enhanced Z80. And they made it as a K-Pro drop-in kit that, again, when I talked to K-Pro people, they never heard about it because they didn't advertise it very well back then. In addition to CP/M at the time on the Z80, there were other companies that were making operating systems. TurboDOS was like a CP/M replacement, but there was actually competitors to NPM. One was called Oasis. Does anybody here remember Oasis? A company in Los Angeles contacted me because they liked the LET, and they had a 10 serial port expansion board for it, and it didn't work, so they hired me to fix it. I did, and then I got them to give me a couple of extra copies, and I used the extra serial expansion board for the accounting company. But the LAT board did not come with NPM, and you couldn't buy it if you wanted to. But what I did is I sat down and opened up the book and implemented the XIOS, which is a lot more complicated than a BIOS. It took me months, but I pushed and got through it, got it to work, and that was in 1986, and that's really the start of this journey, was that I created my own implementation of NPM, but it was the straight one, straight from Digital Research. Several jobs later where I was disconnected from, the CP/M world and not doing any vintage work. In 2005, I became aware that Zilog of the eZ80, even though it had been out a couple of years, I didn't hear about it. And when I saw what it could do, I began to dream of using its high performance facilities to code a supercharged version of NPM. But there wasn't any hardware that it could put immediate to use. There wasn't any commercial products then. There are now. The Argon is a real popular one, but it uses a different version of the eZ80 than I've been using. But the biggest issue was the need for more than just 2 serial ports and a mass storage capability. So I knew that without that, I wasn't going to have a system. So I sat down and on the development kit, they have an expansion interface, and I designed an extension board and then wire wrapped. Wire wrap is really good when your design is constantly changing. If I laid out printed circuit boards, I probably would have purchased 50 different versions. The nice thing about wire wrap is you can take a wire out and move it to a new location in a few minutes, as opposed to waiting a couple weeks for a new version of a PCB to come in. This extension board that you can see here adds 4 more serial ports, so I have the potential to make a 6-user system. And then for mass storage, I picked a compact flash. And so I designed the compact flash. The board took a couple of years, and my wife told me that she was sick of hearing the wire wrap gun, click, for hours and hours. So then, to get NPM to work on the Z80, you could do a straight implementation. It's just that it wouldn't do anything more than what it could do before. You would just use the eZ80 as if it was nothing more than a simple Z80. But I wanted to use all of the advanced features. So I had to modify the microkernel to save all 24 bits of the registers that have been expanded from 16 bits. The eZ80 includes a second stack pointer, and then the eZ80 features 16-bit classic Z80 processes, and then the new 24-bit eZ80 processors that treat all 16 megabytes as just one big bank of memory. And so that was fun. It didn't really take long to get a version working. I had to really understand how it uses its special features to switch back and forth. And then, you know, the compact flash driver, I designed the driver from, you know, the specification. And it didn't take long to get a first version, but boy, it took a good year to get it reliable. It took a long, and you get it to work with more than one particular compact flash. But once, you know, there's a point when you develop software where it's reliable enough and you can't think of anything to add, and you can actually feel free to work on something else. But when it doesn't work reliably, and you would rather work on other things, you know you have to just get this thing reliable because you can't go forward with something that you can't depend on. So as an NPM system, this is just a quick summary of what it gives versus what it provides versus you know, the older hardware that it has. So you have a CPU running at 50 megahertz, and all of the instructions take much fewer cycles to run than a Z80. But it had a megabyte of flash, a megabyte of RAM, and then I put in the compact flash. And then what I did is in the compact flash, I implemented all 26 available drives A through P, and I implemented them as 65 megabytes each. So CPM limited drives to 8 megabytes, but one of the things that NPM did was it greatly expanded. And so basically I have 1.7 gigabytes of mass storage. Let's see, and then I already talked about the serial ports. So this is what you get with classic CPM. This is just an explanation. All CPM does is that when you enter a command line, you know, if you say WordStar, it then goes out to your mass storage and sees if it finds a file called wordstar.com. And if it does, it loads it in and fills it in the yellow area that you see called the user area. And then the other areas are the operating system. And so you can see that CPM applications never really have complete use of the entire 64K. What programs like WordStar certainly do is as soon as they get running, the first thing they do is figure out how much of the TPA is available, and then they fill it. Because WordStar can obviously work on files that are huge, you know, megabytes if you want to, but it still has to roll them into the user area and roll them out, so it is working like virtual memory. It works on the immediate stuff, but as it goes through the file, it's constantly writing out to the mass storage back and forth. So if you have a small user area, it has to do more of that and it slows it down. A bigger user area speeds up any application that can use the memory. So this is from the NPM documentation. This kind of explains how it organizes the banks. So the bank 1 through bank N are the user banks. And each user has a bank, and the applications are loaded in the banks. And bank 0 is reserved for the operating system. And then within the operating system bank, these are all the different modules that are loaded in. And this right here that you see is, from here up above, is the common memory. This memory is always in place regardless of the user bank because the operating system has to always be, mostly its data structures have to be constantly accessible regardless of which user is executing. And so one thing that NPM suffered from is that the amount of memory available for TPA was less. Altos never sold an NPM version that was less than a 48K TPA when CPM systems were typically 56K. So in my development progression, as I mentioned before, I rewrote the microkernel. I got the, after I got the compact flash driver going, I had to do a blocking, deblocking, and all that means is that CPM and NPM, their world is files are 128-byte records, 0 to N records. And compact flash is 512 byte records. And so you have to reconcile that, and that's what a blocking, deblocking driver does. So I had to write one from scratch, and it took debugging and such. And then I had to write serial port drivers, and that actually took quite a while to get the flow control to work correctly. The terminals will tell you that you got to slow down, you're going to overwrite me. And so I had to refine the drivers, and I got them writing. And I managed to write my drivers so that the storage area for the buffers was not in the system, or in the common memory. It was out in system memory, so it didn't really take away from the memory that was available for user applications. So one of the modules is called the terminal message processor, and its whole job is to take the command line that you enter. When you say wordstar.com and you hit return, the first thing it does is send that off to another process inside NPM called the command line interpreter. And its job is to check that command line to see if it makes sense, check for a file match, and then the CLI loads that application. It finds a user bank, loads it in, and then it creates a process and allows that application to run, and then it gets ready to load the next user who may want to do the same thing. But whenever you create a new CPM hardware, if you design your own board, whether it's CPM or NPM, the one thing that you have to deal with is it doesn't have any software on it, for, applications in particular. So how do you get it on it? So the way to do it is I found on GitHub a very simple X modem driver, and I modified it because it had a bug in it. And right after I downloaded and figured out the bug, I went back to the GitHub site, and 7 other people reported the same bug. Like, if I'd only waited a little bit, I wouldn't have had to figure out where the bug was. Somebody else could have done it for me. But I downloaded just enough software so that I could, I guess the priority was like a copy, a program, they call it PIP in CPM, Peripheral Interchange Program. But the other one that I loaded in was Z modem. So Z modem is the last version of X modem. A guy named Chuck Forsberg created it, and it's actually written in C. But the beauty of it is that you don't have to type in the name of the files. You can give it, star.star, and you can copy entire directories without having to count them or know how many are in there. And so the way I get software back and forth, I do it on my Mac, but it works identically on a PC. You just need a COM program that supports Z modem, and virtually all of them do. And so I have on my Mac at home this folder that has a folder for A0, A1, all the way up to A15, all the way up to P0 and P15. They're just folders of the contents. And that's how I do backups, and that's how I introduce new software that I find I download it on. But until you can get Z modem working, and you're stuck with X modem, which you have to type in every single file, and it gets really, really old. So there's a tremendous incentive to get Z modem working. And I can tell you that for years, I couldn't figure out why Z modem kept crashing. And I kept trying to figure out if I wasn't implementing the changes in Z modem. And when I finally figured out what was going on, is that the XIOS jump table is different than the one in CPM. I just presumed it was the same, but it's actually offset by 3 bytes. And I said, really? And when I was pouring through the code, why is that at, offset 8 instead of offset 5? I put it, and I couldn't believe it. It came up, and I did without it for years. The last thing that, and was the most difficult thing, was to rewrite the part of NPM that manages the process tables, or the process descriptors, as they're called, and the queuing function. Queuing is, for instance, one of the ways that you keep users from clobbering each other is only one person or one user at a time is allowed to use the disk subsystem. So if you have some files that you want to write out, you have to gain access to the disk subsystem. And what you do is you send a message to, it's actually a process called, or it's actually a queue function called MX disk. MX stands for mutual exclusion. And so as soon as you're done with the disk, then you write it back out, and that frees it up so somebody else can use the disk subsystem. When you look through the source code, it's not real evident how it works. How I learned how it works is actually watching it work by using the debugger and single stepping, like, that's how it works. But the dilemma is that the Q source code, the process management source code was so huge, and you can't just change a little bit and try it out and then change a little bit more. It's an all or nothing. Because as soon as you know, like I had to change the data structures from being 16-bit data structures to 24-bit data structures. But there were some exceptions to that. And I spent just the typing it in to change the stuff to work with 24 bits took 2 weeks. And then when I couldn't see anything else that needed to be modified, then it's a moment you dread. It's time to try it. So you try it and you think, it's not going to work the first time. But because you can't think of anything that you didn't, and I reviewed it like 7 times to see if I overlooked anything. I reviewed it so thoroughly and I couldn't think of anything. This should work. And so it's not going to work, but you hope it's going to work. You try it, and it wasn't even close to working. So it took another several weeks to one by one troubleshoot and figure it out. But eventually I got to the point of where it all just worked, and it was like a tremendous joy. So here are some pictures of the development system. So on the left is the host board. And you can see, if you look in the middle on the left, it says Connexent modem. Connexent came from Rockwell, and Zilog at the time was hoping to convince customers. They worked with Connexent and made a kit. You could buy a modem kit, but they were hoping that the eZ80 would be used for modems. The Z280 was used by Hayes for its modems a few years earlier, and they hoping to grow that. But of course, in 2001, modems were already on the way out. DSL and cable modems were already taking over. Now, on the upper right corner, you can see the sockets where that small board is the CPU module. It includes a megabyte of flash, 512 megabytes of high-speed static RAM, the real-time clock battery is there, and then an Ethernet media access controller. You still have to put an Ethernet PHY, as it's called, PHY, but you can run fast Ethernet, or it's also called 100 megabit Ethernet on a Z80. It's fast enough to handle it. In fact, they have some sample software where the eZ80 can actually run a website with Java and everything. And fast Ethernet is most appliances that you buy at home are, many of them run fast Ethernet, but some of them run the 10 megabit Ethernet. So it's actually pretty impressive that it can keep up with that. So this picture shows the CPU module plugged into the host board. And then if you look in the lower half, those are the expansion, where an expansion board goes, and it shows the signaling that's available. So that's how I designed my expansion board, is that it plugged into the various CPU signals that were available, so that I could, have the compact flash addressable by the CPU. And then this you can see here. But I wanted to show you this. This is the underside of that board. So that's months and months of wire wrapping. And fortunately, I had a good wire wrap kit that had lots of different colors. I've seen other people that only had access to one color wire, and I really felt sorry for them when they had to trace down wires that aren't at the right place. So what I gained by the eZ80, and this is that compared to the Z80, the eZ80 basically has the same features of modern CPUs. They haven't really changed much. When you introduce a new CPU, they're going to be faster. They're going to have, Apple is doing the M1 through the M4 ARMs. The one thing that you expect when you hear about a new CPU that's rolled out is they all have a JTAG interface, which allows you with the development system to set hardware breakpoints. And you can do things that the most sophisticated, with a Pentium, you can single step through source code. You can do that now with Z80 source code, and that has helped tremendously in troubleshooting. Because sometimes when there's no rational explanation why something isn't working, you really, instead of trying to rack your brains out figuring out what part in the source code is wrong or typed wrong or just not, what you actually have to watch things work. And so that's really difficult on a Z80 because you can't single step through source code. All you can do, the best you can do, or what we used to do back then, is to load them in with a debugger that would single step through, but you didn't have your labels. You didn't know, okay, this is pulling something from address 4C22. What is that? And you'd have to go to your source code. Oh, that's this label. So when you single step through source code, everything's there and you can just watch it work. And so it's actually been quite a joy to understand. That's how I understand how queues work, is to watch it work step by step. The other thing that, the reason why it's 50 megahertz is that's really the fastest speed you can hope to run with the fastest available static RAM. It fits like a glove, right? For a long time, the fastest static RAM you can get for at least byte-wide and 16 bits wide is 10 nanosecond access time. And the Z80 runs at 50 nanoseconds and it fetches one byte from memory or writes 1 byte every 20 nanoseconds, but you need the difference between 10 nanoseconds and 20 nanoseconds for your decoder logic to work. The other thing is the CPU has onboard flash, a little bit of RAM. I was using it for a while, but I don't need it anymore. But when I make a change and want to test it, the assembler assembles everything within 3 seconds, all of the source files, and it's what like 9 different source files. It links them and creates object code within 3 seconds, and then to download it takes about another 20 seconds. So sometimes when I'm single stepping, oh, that's a mistake, I'll type it in, download it, and I'll do sometimes within 10 minutes download and try 15 different versions. The way it used to work on a CPU of the 1980s vintage is you would create an image file and you would download it to an EEPROM programmer. If you had some EEPROMs that are already erased. If you ran out of erased EEPROMs, you had to wait about a half hour. And you put them in an EEPROM eraser to clear them out. And then the EEPROM programmer, the early generations would take 10 minutes to write. The smart ones could write one in a few minutes or less than a minute. And then you'd have to plug it in and power it up. And so your cycle time of making a change and testing it was, in a 10-minute period, you were lucky to get 2 versions done. In that version, I could get 15. And so that's the difference between whether troubleshooting is fun or not for me. And the other thing that, so the CPU has a built-in flash, and people that know flash know that one of the aspects of flash is that you don't have unlimited writes. Even if you buy a flash drive, the very best flash drive is you have up to 100,000 times you can write any one location. And the way that, disk drive replacements work is they implement a software feature called wear leveling. Is they look for how many cycle times have been in a location, and they'll remap so that, if you do your calculations, it might be centuries before you could actually hit 100,000. But if you don't use the wear leveling, and you have something that's like in the main directory, like if it was on a Unix system where the file swapping file was, you could, the swap area on a disk mass storage, you could, in a matter of weeks, wear out a flash memory. So on this CPU, because of the type of flash memory, it has a lower amount, it's 10,000 cycles. And even that's not enough to worry about. So for the first couple of years, I would create the image on the CPU flash, which is far more than I need. It's 256K. But what I did is I got smart, is that I used the flash memory that it's actually on the underside of this CPU module. It's 2 megabytes and it's a standard 100,000. And so, I think in all the years I've probably only done maybe 1,000 or 2,000 cycles. But it's something you think about, and now I don't have to think about that. So the other thing is that the eZ80 is still in production, and the last I saw one of the distributors, they had like 800 of them in stock, and it's still used in TI calculators, and so that's the Z80, as most people know, Zilog announced they're not going to make anymore 2 years ago. And the reason is that no fab wants to deal with the low resolution architectures that the Z80 requires. So it kind of makes sense from a business aspect. But things that I haven't used is I haven't used the Ethernet MAC, and I haven't used the serial peripheral interface. That's what SPI stands for, or I2C. And you can see that, let me jump ahead here. On the future development possibilities, that's what makes it possible to make a physical interface for using Arduino daughter cards. They call them shields. But you can get, if you just do a search on eBay or the internet, there's all kinds of different companies, and there's hundreds, if not thousands, of Arduino shields that can do all kinds of things, and they all have the potential to be written using this software. So in so now that I've actually got most of the software done, I'm actually thinking, what should I do next? There's no real big software thing that needs to solve, so I'm probably going to start putting on my hardware hat and lay out a board that represents not really this daughter card that goes in the development system, but a standalone that would it would be probably not much bigger than the CPU module. I started it a number of years ago, but I got software is more fun than laying out boards, so I got sucked back into that. But I have added new system calls, and one of the ones that I've penciled out in paper is one I call set get OS mode. I already have a way that when an application comes to life, because many applications interrogate and say, which operating system am I running under? So I got frustrated because I would run a CP/M Plus application and it would say, requires CP/M Plus. And I have there's no reason why it wouldn't run under NPM. So I actually found a way that you can set file attributes on applications so that it tells the operating system, if anybody asks you what operating system, say you're this. And so now all the CP/M Plus applications that come with CP/M Plus, they work fine on the NPM system without that ridiculous thing. So anyways, I spec'd in there that the operating system would say it's CPM 2.2, NPM, CPM plus, or CPM 3. But one of the things that occurred to me is there's at least 3 different 6502 emulators, or simulators, however you want to call them. They were written back in the 80s and one was written in the 90s, that I could actually say I'm a 6502. The eZ80 has enough horsepower that it would run 6502 software faster than a 2 megahertz 6502. And there is a 6502 version of CPM, and Microsoft actually published MBasic for 6502 CPM, and it's not hard to find it. So that's a possibility. In my retirement, there's so many things that are possible. I'm not going to get to all these things, and that's why I published all of my code on GitHub, and I'm hoping that some people will say, send me your source code, I'll do this, but they have to have hardware to run on it. So that's why, for me, I think hardware is the next big task that I'm going to take on. The Zilog development system comes with a TCP/IP stack, and it occurred to me I could actually make NPM work with it in the same way that Parallels works with a Macintosh to run PC software, is that you can make assembly calls within C, and so I could make it go back and forth between, when NPM is idle, it goes back to this TCP/IP stack. With that, I think I'm running into the next talk. So thank you for staying throughout. And if you have any questions, the best thing to do is to come and visit me. I love questions. Thanks for coming.